So I think one of the most common questions that a math teacher gets, other than like, why do I need to know this, is who comes up with this stuff, right? Like, we introduce a crazy definition and you're like, who in the world figured this out? Well, for this problem, for Taylor and Maclaurin series, I have got you. So the two guys who really helped develop this were Brooke Taylor and Colin Maclaurin. So just a little bit about them, right? You can enjoy those headshots of them over on the side, right? Brooke Taylor was born in 1685. He was from a wealthy, cultured family in England, and he went to Cambridge University and got a law degree. And he also learned about mathematics there. So in 1712, he not only stated his method for infinite series, but then he was also elected to the Royal Society for Mathematics and appointed to a committee to adjudicate the dispute between the Leibniz and Newton kind of conflict about who came up with calculus first, right? That was a major debate, and that's why we kind of refer to them both as the fathers of calculus, right? Because it's kind of unclear about who developed it first. Big controversy. So Taylor is given credit for conceiving the concept of the calculus of finite differences, which is for finite differences. He also came up with the tool of integration by parts and what we call now Taylor series representatives. And he died at only the age of 46. So by the time he was 46, he came up with all of that cool stuff that we use a lot today. And then this guy, Colin Maclaurin, was born in 1698, so a little younger than Brooke Taylor, and he was born into a minister's family, and I'm not even going to try and pronounce that county of Western Scotland. Maybe I'll try just for your benefit. Greelishire, if, I don't know. Google it, and maybe Google Translate can do it for you. So he was actually a child prodigy in math, and at the age of 11 went to the University of Glasgow, and at the age of 19 he was elected to become a professor of mathematics at the University of Aberdeen. And 2 years after that, he was also elected to the Royal Society of London and came to know Isaac Newton. And it was Newton who recommended to the University of Edinburgh that Maclaurin become a professor of mathematics there, which he was at the age of 27. Imagine becoming a professor of math at the University of Edinburgh at the age of 27. It's insane. But in 1740, he shared a French Academy of Science prize with Leonard Euler and Daniel Bernoulli, two massively famous mathematicians. So he's definitely like a contemporary guy. Like, he's definitely up there in the world of mathematics. And then in 1742, he wrote a 2-volume treatise defending Newton's mathematics as a rebuttal to Bishop George Berkeley, who had claimed that Newton was using faulty reasoning. So he was a big supporter of Newton. In that book that he wrote, defending Newton, is actually where the special case of Taylor series appears, which is now what we refer to as Maclaurin series. Maclaurin also died very young. He died at 48. His health was destroyed after he participated in the defending of Edinburgh when the supporters of King James II marched on the city. So he died, protecting what he loved in Edinburgh. But anyway, enough about those guys. We're going to actually do some stuff with Taylor and Maclaurin polynomials now. So we're going to use this as our first example here. So we're going to suppose that f is a function with continuous derivatives and that these statements are true. So f of 2 is 3, the first derivative at 2 is negative 4, the second derivative at 2 is 7, and the third derivative at 2 is negative 5. So we're going to use that to write the Taylor polynomial of degree 3 for f centered around 2. So all this tells us is that we need to get, we're going to go out to the third derivative of c over 3 factorial times x minus c cubed. So for this first example, I'm going to write everything out. We're going to be very thorough about it. So we want the third degree Taylor polynomial. So you could use that p notation from our definition. Some people also use t for Taylor, but we're just going to use p. So we want a third degree Taylor polynomial, so we're going to make that little subscript of 3. And that's going to be equal to f of c plus the first derivative of c times x minus c to the first power plus the second derivative of c over 2 factorial times x minus c squared plus the third derivative of c over 3 factorial times x minus c cubed. And then you're just going to kind of plug in with what you know. So we don't actually have to do much math here because they gave us all this information. So our third degree Taylor polynomial for this particular function is going to be f of c, and our c value is going to be 2. I'm going to actually back that up there. I don't want to label it as x equaling 2. I want that to be c equaling 2. Okay, so f of 2 we were told was 3. And then our first derivative is going to be negative 4. So I'm going to actually switch this out. Times x minus 2. And then the second derivative of 2 is 7, so plus 7 over 2 factorial times x minus 2 squared. And then our third derivative is negative 5, so I'm going to have minus 5 over 3 factorial times x minus 2 cubed. If you want, you could simplify that further, because 2 factorial is just 2 times 1, which is 2, and 3 factorial is 3 times 2 times 1, which is 6. So you could change the denominators to not have the factorials, but you don't have to. Right, so that's going to be our third degree Taylor polynomial. Okay, so then maybe we're given a problem like this one where we're asked to find the sixth degree Taylor polynomial for f of x equaling the natural log of x centered at c equaling 1. And then we're going to use that to approximate the value of the natural log of 1.1. Okay, so the first thing we need to do is we probably need to figure out all these derivatives. So we have f of x is the natural log of x. And then I also need to know my f of c. So f of 1 is going to be the natural log of 1, which is 0. Right, and then I need to know, I'm going to actually zoom in and make this a little smaller just so I can conserve some space. So my first derivative of the natural log is 1 over x, or x to the negative first power. Right, so then my f prime of 1 is going to be 1 over 1, which is 1. Right, and we're going to go all the way down to the sixth derivative. So this is really good derivative practice. So the second derivative is going to be power ruling that. We're going to bring down a negative 1, x to the negative 2. Give ourselves a little space here. This is going to be negative 1. Right, we're just going to continue this pattern. Finding the third derivative, we're going to get 2x negative cubed, which is 2 over x cubed. So our third derivative at 1 is going to be 2 over 1 cubed, which is 2. And now remember, when you get into higher order derivatives past 3, we use that parenthesis notation. So that's our fourth derivative of x is going to be power rule again, negative 6x to the negative 4th. And evaluating that fourth derivative at 1, we're going to get negative 6 over 1. And then we're almost there, right? 2 more derivatives. So my fifth derivative is going to be 24x to the negative 5th. Which is going to give me 24 when I evaluate that at 1. And then our last derivative for this problem is the sixth derivative, since we want to find a sixth degree Taylor polynomial. And 24 times negative 5 is going to give us negative 120, x to the negative 6. And then evaluating that at 1 is going to give us negative 120, of course. Okay, so now we're going to use that to put together our Taylor polynomial. So our sixth degree Taylor polynomial is going to be f of 1, which is 0, plus our first derivative times x minus 1, plus our second derivative, which is negative 1. So I'm going to put negative 1 over 2 factorial times x minus 1 squared, plus our third derivative, so 2 over 3 factorial times x minus 1 cubed. And then our fourth degree term is going to be minus 6 over 4 factorial times x minus 1. Hang on, Lincoln's barking, I'm sorry. To the fourth degree. Then I'm going to bring this down to the next line just to give myself some more space. So then I'm going to have plus 24 over 5 factorial times x minus, oh, I keep doing this, x minus 1 to the 5th power. And then my last term is going to be negative 120 over 6 factorial times x minus 1 to the 6th power. Now, if you know anything about factorials, I'm just going to write what their values are underneath of them. Right, 2 factorial is just, I'm going to give myself a little bit more space here. 2 factorial is really a 2. 3 factorial is 6. 4 factorial is 24. 5 factorial is 120, and 6 factorial is 720, right? So if we actually simplify this, our 6-degree Taylor polynomial actually simplifies, right? 0 doesn't matter. We have x minus 1 minus 1/2 times x minus 1 squared plus 1/3 times x minus 1 cubed minus 1/4 times x minus 1 to the 4th power plus 1/5 times x minus 1 to the 5th power minus 1/6 times x minus 1 to the 6th power. So there's the first part of our answer, right? We want to find the 6-degree Taylor polynomial, so we did that. And then we're going to use it to approximate the natural log of 1.1. So the natural log of 1.1 is approximately going to be equal to the 6-degree polynomial at 1.1. And that's just equal to, you could plug that in. I can't find my calculator all of a sudden. There it is. Right, I'm just going to type this into my calculator, which seems to defeat the purpose of the Taylor polynomial approximation, but we have 1.1 minus 1 minus 1/2 times 1.1 minus 1 is just 0.1 squared, and then we have plus 1/3 times 0.1 cubed minus 1/4 times 0.1 to the 4th plus 1/5 times 0.1 to the 5th. And in theory, right, you could do all of this by hand, but we have technology, so I'm going to use it just to get what the final value is. And I'm thinking I typed something in wrong because I have a different answer than what I had in my notes. I'm going to scroll back through. Oh, there it is. I have an x instead of a 4. Nope, that's not it. Well, this is embarrassing. Probably should have typed this into my calculator before starting this problem. Plus 1/3. I think I'm right. So we got 0.0953, and if we look at the actual natural log of 1.1, Right, so I'm actually going to bring up my calculator screen, and I didn't use the one on my computer here. I used an actual calculator, so bear with the quality of this picture. Right, you can see my last two numbers, right? Our Taylor polynomial approximation is that second to the bottom line, and the actual